ladies and gentlemen. Welcome to our class. First, the question, did all the download problems resolve? Can you download the files? Can you download the video if you want to? There was some problem, just play around with the right and left mouse click and then it will work. So everything is fine. Also, I put in the slides as a six-pack because I was asked to do so. That functions, everything fine. Any other technical things, any other technical problems you want to solve?
The videos still download.
Oh, you cannot download it? Oh, it is possible. I tried it out, people tried it out. You just use the other mouse click and use another tab. There are 3 different tabs. Go to the right-hand tab and let you help you from your colleague here. Because women are just better in these technical things. You have to accept that, right? Okay? Nobody smiles. Well, okay, next joke next time. Good. So I have a list here for the horticulture science students, MSc 13. And that is the list where you put in your name for the presentation of research projects. Right? That's for the 19th, 26th of January and 2nd of February. You know what I'm talking about. I told you about that in the beginning. Okay? If not, read just the first or second slide. So you have to print your name in here and the research topic. I don't know exactly how many students there are, whether it's 18 or 19 or 20. I have 18 slots here. If one is, there is a 19th student, write down your name and then I'll find a different date for that. Please do that during the break. Once the list is full, I will put that on the internet, so you don't have to write down which day you took. Your research project you should know anyway, right? That doesn't hold for the engineering students in water engineering, okay? Because you do written essays, 2 pages, right? It's only the horticulture students that give an oral presentation. Is that somewhat clear? Okay, I'll be here during the break and help you if you have any problems. All right, so last time I finished inductivism. Inductivism is that theory of science. It's an idea of what science is, and the central idea of inductivism is that one should start from secure beginnings, namely singular observation sentences, and there are usually no problems in identifying these sentences and finding out whether they are true or not just by observing facts. And then the problematic step, a rather problematic step, is then to generalize from these singular statements to the general statements science is interested in. Science is interested in these general statements because we need them for any kind of prediction, explanation, or technical application. Therefore, we are interested in the general statements, and therefore we do have in any scientific, in any theory of science, we have the problem of how to justify these general statements. Now, the inductive way to these statements is, as I said, so-called inductive generalization, and inductivism tells us that these inductive generalizations, because they are risky, you can make mistakes in them, you have to fulfill 3 conditions, and these conditions I discussed, and inductivism tells us that if you fulfill these 3 conditions, then you are allowed to generalize and get the general statements, and when you have these general statements, you can explain, you can predict, and you can technically apply them. This is the position. It's very plausible. If you look at certain examples, it's really plausible, and also these conditions are plausible. I told you then that the development of this position, how I presented it, was a normative development in the sense that I showed you that it's reasonable to have such a theory of the sciences if the sciences are supposed to be and should be reliable, especially reliable knowledge. And then it's plausible to have such an image of science. This is a normative treatment, being in contrast with a descriptive treatment. In a descriptive treatment, I would have done something different. I would have described actual practices of the sciences and then told you, look, this is how science proceeds if you look into the labs and so on. But I choose a normative procedure, and that is because this position has been developed in a normative way from its beginnings, and therefore I presented it that way. I then showed you, and this is something which you just now notice and remember, because we will see that later other positions in the philosophy of science will proceed mainly descriptively. They will say, look, these normative procedures, they don't really work, and we'll find that out. But you have to be aware of this fact that there are two different ways of doing philosophy of science, and that the first presentation of a position, namely inductivism, proceeded in this normative manner. Okay. I then showed you that this quite plausible position of inductivism faces a number of difficulties which you may not have noticed when you heard the position first, but which have to be taken seriously. And one of the things, well, let me repeat two of them. One is that if you look at 20th century science and 21st century science, say in the biosciences, molecular biology, and you look at things like the structure of DNA or other high-level scientific hypotheses, then you see immediately that it is absolutely impossible to get these hypotheses by generalization from singular observation statements, because these things, very general statements, don't say anything about something really immediately observable. So you can't get them by generalizing from observable stuff. They speak about highly theoretical entities. The concept of gene, when it was introduced in the beginning of the 20th century, was an absolutely purely theoretical, hypothetical entity. Nobody knew what a gene was. It was just in genetics, it was introduced as a theoretical entity that people reasoned there must be something like a gene responsible then for the different phenotypes that you get after crossing experiments. And it was purely hypothetical. Nobody knew what it was, materially speaking. It was only in the 1930s that people start to reason about what the material nature of a gene could be. Nobody knew it. And until the late 40s, people thought it was a protein. Yeah, everyone believed that genes are something like a protein. They did experiments and they believed, well, there must be proteins, because why? Well, they knew that was something like DNA, but DNA was believed to be a too stupid molecule. It was just a periodic molecule, so that you cannot store any information on it. So people believed that the genetic material must be a protein, right? And then only later, in the late 1940s, 1949, people came to the conclusion, oh, it could be DNA, but we don't know its structure. And then they made experiments, complicated experiments, with the X-ray diffraction, and then they discovered in 53, Watson and Crick, that the DNA was this double helix structure. But it's absolutely obvious that there is no direct observation from which you can generalize and then come to the conclusion DNA has a double helix structure. It's just no way. So inductivism, if it was ever a good theory about the science, can only be a good theory of the science in very early stages, where you have very simple laws that really describe observable things, observable correlations, like the one, say, the gas law, P times V is a constant, the ideal gas. There you can observe the P, you can measure it, you can observe and measure the volume, and then you can say, okay, I measured that in many cases, and then I generalize to the general gas equation. There it is plausible. And that was the situation in the 17th century, when people measured things and then made generalization. At that stage, it was at least very plausible, and therefore everybody believed it, at least until the 19th century, that science, the natural sciences, are enterprises characterized by the inductive procedure. Therefore, they were called the inductive sciences, right? In contrast to the deductive science of mathematics, right, which is a different form of science. Okay, so this is the first problem, that although inductivism may have been really plausible in the early parts of the development of the sciences, it's certainly not applicable to the more advanced parts of science, where you have general laws or general statements of a character that it just concerns non-observable things, like the structure of DNA, which you cannot directly observe. By now you may, but at that time when it was introduced, you couldn't. Or if you look at, even if you look in physics at some of the more abstract equations, if you look at electrodynamics, if you look at Maxwell's equations, I mean, there are things involved that have no direct counterpart in nature which you can measure. I mean, there are potentials and stuff like that, and it's just impossible to generalize it. So the process by which you find these more general things of modern, of science of the 20th century, like Schrödinger's equation or Maxwell's equation from the 19th century, or the structure of DNA and so on, they refer to things which you cannot observe, and therefore it's impossible to gain them by an inductive procedure, so we must have a different theory. I mean, it's just not applicable to the very modern parts of science. That's one of the arguments. That's a very strong argument, because I think, I mean, you cannot evade it. I mean, there is just no way to come from the observable by generalization to the unobservable. That doesn't work. If you talk in Schrödinger's equation about structure of DNA, about something unobservable, you cannot get there from generalizing from the observable. It's just impossible, right? That's one point. And the other point is a more theoretical one, but also a very important one, because it's very important for the position that I'm going to develop today, is the observation that although it is so wonderful if you have the idea that you start in science with something which is absolutely secure, right? You say we want to have good knowledge, right? Reliable knowledge, secure knowledge. So when our starting point from which we start must be provide a very firm basis. It must be very secure, right? And then the idea, okay, why don't we start with something which is absolutely not controversial, namely observation sentences about particular things, right? Then you say, then I'm on a very safe ground. Nothing can happen. I mean, if we talk whether here is a watch, you may see it or may not see it, it's here, I put it back again. And whether when we say, well, is there a watch on this desk? Then everyone who looks at it said, yes, there is a watch on this desk. And we can have no disagreement. So it seems to be extremely secure, right? No problem. And it's an extremely attractive idea if you think of science as something that builds up from very secure foundations. And then you have these singular statements, and from there you then generalize and do whatever you want to do. The point simply is, if one looks a little closer, that this idea of having this very firm and theory-free basis, right? No theory must enter, because theories may be wrong and you may not know it, right? Therefore, it's so attractive to say, no theory, I'm just observing. Here is a watch, that's it. No theory involved, no risk. Right? Therefore, we can agree. And that sounds extremely convincing and nice, you know, to start with such a firm basis for science. But the point is, once you look a little closer, it's an illusion. Right? The first illusion is, in describing what's here, you're already using concepts, and these concepts are risky, because the concepts can be, bad concepts. For instance, if you say, in an earlier phase, if you say, yes, I'm observing this fish here and it's a whale, right? I'm observing this fish, a whale, right? You see, you have an hypothesis there, namely that whales are fish, and they aren't, right, in the biological sense. So by using a concept, you run already a risk of making a mistake. And it is just not a theory-free observation when you say, yes, I'm observing this fish here, this whale, even if everyone agrees. Yes, there is the classification inbuilt here that whales are fish, and they aren't, as we know today, right? So even these innocent-looking observation sentences carry some load of theory, and once you look a little more, the procedure of how to generalize, then you get in trouble everywhere, because theory enters everywhere. Once you say, yes, I have to take care only of the relevant observations, right? You don't want to have irrelevant observations, because then you can't stop looking everywhere and observe everything. You must only concentrate on the relevant observations. And once you ask yourself, well, which are the relevant observations, then you are entering again theoretical elements that could be false, right? So the point is what one learns from the failure of inductivism in that respect, namely that it is an illusion to start from something completely theory-free, is that we have to have an alternative to inductivism that takes from the very beginning very seriously that whatever we do in science, from wherever we start, theoretical elements will be present always. Right? There is no way to avoid theoretical elements in science. And theoretical elements implying they could be false. Right? That's the problem of theories. Right? Theories are wonderful, they're general and everything, but they could be false. And we don't want to have false claims in science, we want to have true claims in science. And the problem is then, how can we deal with that, right? That we have to somehow exclude false theoretical claims and gain the true theoretical claims, or at least acceptable theoretical claims. So the point is that the solution that inductivism tries to do by saying, yes, we just avoid any theory from the very beginning in order to deal with that problem, that doesn't work. And so one has to have a position, a view of science that says, okay, we have to take seriously that whatever we do in science, there will be always theories involved, theoretical elements. And what we have to do is we have to accept that fact and deal with it, you know, and be critical about it and try to eliminate false theories and keep the good theories. But it's not a feasible strategy to say, I avoid any theory at the beginning at least. That doesn't work. It just doesn't work, right? So this is the position of inductivism, which still, by the way, many people in the sciences sometimes believe it is okay. And I mean, very often it is true that procedures in the sciences look similar to inductivism, namely that you say, okay, I have to have many data and I have to observe them carefully, and then I try to generalize from these data. I mean, many of the procedures, if you look at certainly certain aspects in horticulture science, in building greenhouses and all that, when you collect the data, and also when you look what are the relevant variables for the behavior of certain plants, their growth or whatever they do, and diseases or so, you do make experiments and you change your observing conditions, and it looks quite inductively, and then you try to generalize from what you see. So many aspects of science do indeed resemble that. But once you think that by inductivism you get a general, reliable view of what science is, then you are mistaken. Right? That doesn't work. And what we'll see now in the next position is an alternative to inductivism that takes care just of these problems that I mentioned. Right? So we've learned something by saying, okay, inductivism doesn't work. It's not that we are left empty-handed. We have something, namely we have the imperative of taking theoretical elements seriously in the sciences at all levels, right? At the level of observation and at the level of general hypothesis, medium range, or big theories. Theoretical elements are everywhere. We have to take them seriously, and we have to take precautions to avoid wrong theoretical elements. That's the trick now. That is our task. And deductivism will be the position that takes this task very seriously. Okay, I now tell you something a little about the literature, and then you will have the opportunity to ask questions. So the literature, the general book that I recommend to you if you want to read something. I told you it's not necessary, but if you're interested in these things, then you can read something, and this is, according to my judgment, the best book that is around accessible for beginners. What is this thing called science? It's a very successful book. It's been translated in 15 languages. And here for the beginning, inductivism and that stuff that you find especially in chapters 1 to 4. Okay. So if you're interested in reading something, it's also, I don't know how much it is, but it's cheap. You can buy it. Now, if you happen to be interested in historical things, then you may read this. It's also a standard book by John Lucy, A Historical Introduction into the Philosophy of Science. That's an overview over the historical development of philosophy of science from antiquity. So if you're interested in that and said you find people in the 19th century, whatnot, this is the book to read. And then this is a very advanced book. So if you start reading that, you won't understand. If you start reading that, you probably will not understand very much. This is an advanced book. This is the book that in Pittsburgh people use. Pittsburgh is one of the largest centers for philosophy of science in the world, and with an excellent education in philosophy of science. But the master students there in philosophy of science, they have to read this book within 1 year. And once you've read this book, then you know a lot. Okay, but it's just here for completeness. And here is a book that is now not on your printout because I added it now. This is on engineering. What in it? Vincenti is an engineer himself. What engineers know and how they know it. Now, don't be repelled by this one. Analytical studies from aeronautical history. He's an aeronautical engineer, and air is just not the same as water, as the water engineers know. Well, it also flows, but that's about it. Now, the point is that the first chapter is something very good on engineering, right? On engineering knowledge, in its contrast to knowledge in the natural sciences. And also, these studies are very interesting, and you can see certain things about engineering if you're interested in the theoretical treatment of the engineering sciences. This is an excellent book, I believe, and it's available if you can buy it in Amazon. Okay, as much to the literature. And now, are there any questions about inductivism? Is there anything that's left where I say, there's a part I don't quite understand, or some additions you would like to get? No? Fairly clear? Plausible? Criticism was also plausible? Right? That's very important that you understand the criticism. Perhaps you start seeing now why developing a position and criticizing it is something useful, because you learn something in it and that, oh yes, I have to be aware of that problem, right? That's a problem in a theory of science, and that is something you learn nicely in first, believing that inductivism or finding inductivism plausible and then saying, whoops, yes, I didn't think of that, okay? And then now you know how to think of it. Now here is the position of deductivism. And I start in the same way as I started with inductivism, by presenting the basic idea first, that you get an idea of what deductivism is all about. Okay? And as I said already earlier, deductivism is an attempt to develop a position that avoids the difficulties that beset inductivism. It's also historically, it's a reaction to the problems of inductivism. The people who developed deductivism realized these problems that I mentioned to you, and they said, we have to have an alternative. Inductivism doesn't work. We cannot heal that, really. And that there are so many problems with inductivism, and we have to have something else. And that is then the basis of deductivism. Why it is called deductivism, you don't understand at this point, right? I know that, but I'm going to explain it to you, right? The same way as you did not understand why inductivism was called inductivism. In the beginning, you didn't understand that. But I'm told you, and that will be the same here, I will tell you why it's called deductivism. The main, or one of the main points in developing the position is, as I already suggested, that it is accepted that theoretical elements enter science at all stages. At all stages meaning stages of observation, hypothesis building, dreaming up theories, whatever it is. We are always involved in theories, and we cannot avoid it. So we have the problem of controlling theories, because theories can be wrong, and therefore we need very careful control, tight control, that false theoretical elements are excluded. And deductivism is aware of that and tries to deal with it. So it is accepted that theoretical elements enter science at all stages, and that inductive generalizations lack proper justification, right? Deductivism avoids the inductive step, the inductive generalization, because it says, look, we have no real justification for that, right? That's what I told you about this circularity, that it's just not possible to really justify that step. And it would be wonderful if we could avoid this inductive generalization and have something else instead, right? Of course, you can't say, you can't just say, well, I don't want to have any general statements. No. We have to have general statements. But the point is that deductivism says, yes, I want to justify general statements, but not by inductive generalization. I must have something else, right? Because inductive justification doesn't really work. So we have to have something else. Okay. Let's see how deductivism deals with that. And here is the very basic idea. The very basic idea is that deductivism says theories are not built bottom up, bottom meaning observation, right? From theory-free data, and from there you build up by combination or generalization the theories. That is the idea of inductivism. And deductivism says no, that is not right. It is just the other way around. We start with theories, with theoretical elements. We start with them, right? We start with theoretical elements. They are risky, they may be wrong. But what we do then is we test them against data, right? So we do not start with data, observation data, and go then by generalization to the theories. Well, deductivism says that doesn't work. Sorry, it doesn't work. But then we have to do something else, and the something else is one says, okay, we start from the very beginning with theories, with theoretical stuff, with hypotheses. And in order to eliminate those that we don't want because they are wrong, we test them against empirical data, right? So the beginning of science, in that view, is not theory-free observation, but it says from the very beginning, no, from the very beginning, we deal with theories, hypotheses, models, whatever it is, right? I told you in the beginning, these different forms of general stuff, theories, models, correlations, whatever it is, right? Hypotheses. So that is the basic idea that, we don't see how that works at this point, but the general idea is it's just reverting the direction, right? Not starting from observations and then going up to theories, because deductivism says it doesn't work, but just the other way around. Start with theories and test them against data, against observations, against experiments. Yeah? This is already part of how at least the horticulture science people describe their research project, right? Because there is this section where you describe hypothesis, and then you say next what you have to do with your observations and experiments. And that's exactly this idea already built into the structure of your research projects. Do the water engineer people also have such a structure for your research papers that you have to articulate it, situation and then hypothesis and then procedures and data and so on? No. Okay. There is in some sciences, it's a rather rigid form, right, of the structure of the papers or the research project, that every research project has to articulate a hypothesis that is going to be tested, right? That is the case for the horticulture people, right? Yeah. That's the case. And this theory of deductivism is already built in there. So it should look familiar to you, right? That is the reason. It's not that if inductivism was true, then of course people, you would get a different structure for your papers. You would get the assignment, write down all your observation sentences, right? And then tell me whether you fulfill the conditions to generalize. That you don't do in your papers, right? In your research projects, you do something else. You have to articulate a hypothesis. And then you have to tell your supervisor and everyone who reads that, including me, yes, when you give the little paper then, in January and beginning of February, how the hypothesis relates then to the data. Okay, now let's get back here. The basic idea is that theories are not built bottom-up from theory-free data. Theory-free data don't exist, therefore we can't build up from there. But they are deductively tested against data, and what you don't understand here, what that means, deductively tested. You understand tested, but you don't understand deductively tested. I'm going to explain that to you. But that's the general idea, if you want to have, say, in one sentence, inductivism is bottom-up, and deductivism is top-down, right? Just if you want to have one word. And bottom and top is, bottom is empirical data, and top is theories. So you don't go up, you go top down. Okay. Inductivism and deductivism share the view of scientific explanation, prediction, and technical application. That remains the same. So the difference between the two positions concerns the general statements. So that's the main point, right? How do we cope with the hypothetical, therefore dangerous, risky, general statements? How do we justify them? How can we defend them against the possibility of error and mistake? Right? So regarding the view of explanation and technical application and prediction, that's the same. That's basically generally the same, also in the positions that come later. Basically, that's just right according to today's knowledge. That's just correct what I told you about the application of general statements for prediction, explanation, and technical application. Okay, so that's the very basic idea. Now, the point that is now perhaps a little difficult to follow at the first sight at least is this, that in order to establish the testing procedures, right? So we say in deductivism we start with general statements, right? With theoretical statements, hypothetical statements. In order to establish specific testing procedures that you can test these things, these hypotheses must also fulfill a condition. The reason is there are general hypotheses that you simply cannot test against data. That's possible. I give you examples. Right? There are general hypotheses that cannot be tested against data. So if deductivism says, well, science consists in testing general hypotheses against data, the things that are admitted, the hypotheses that are admitted, must be able to be tested. Right? It must be possible to test them. If you have hypotheses that cannot be tested, of course, the whole procedure doesn't work. Right? And the statement here is that these hypotheses that are the candidates for science, because they are testable in principle against data, they are testable because they fulfill a certain condition. And that condition has to be worked out and presented. And that is then one of the next steps, which is called the demarcation criterion. The demarcation criterion tells you what hypotheses, or which hypotheses are possible candidates as scientific hypotheses, candidates because they can be tested. And those hypotheses that cannot be tested are not even candidates for science, right? So science is not even interested in them, whether they're true or not. They're just absolutely not interested in it because they cannot be tested and therefore they cannot be a part of science anyway. You know? Okay. And if you then, well, I've written that down here, what are these other hypotheses, these other general statements that are not admitted in science? Well, they are, in general, there are metaphysical statements, whatever that is precisely, don't worry about that. Religious statements, right, or pseudoscientific ones. That's the point. There are pseudoscientific statements, I mean, creation science perhaps astrology. There are statements that possibly, well, astrology can be tested, I guess. It depends. Well, there are at least statements, you know, and I'll give you an example just in a second, that are articulated in a way that you cannot test them against data, right? Where the data can't eliminate them if they are wrong, or they cannot support them. They are just very strange ones, and metaphysical, religious, or pseudoscientific ones. It's difficult to say exactly what that is, you know, what exactly religious statements are, but for instance, religious statements, typically believers in certain religions, they are not really influenced by empirical data. I mean, if you believe in God, then usually it may happen, everything can happen, and you still believe in God, right? Even if it's very bad. So, for instance, many Jews weren't really much influenced regarding their religious belief in God by the Holocaust. And one can say, well, is that a good God who admits the Holocaust? Oh, I don't really know. Well, I'm not discussing that here in principle. That would be a different class. The point simply is that typically religious beliefs are independent of empirical data, right? Somehow. How people manage that, whether that's good or whether that's bad, is a completely different story. It's simply a description that usually people who have really deep faith, whatever it is, Christian, Judaism, Muslims, whatever it is, usually are not very much impressed by empirical data, right? Your son may die, your mother may die, you may die. Well, that's a different story than if you may die. But whatever happens, I mean, God did it or whatever, and you have a sort of story for that, and it doesn't influence you, right? Or the sun may rise, or may not rise, or that's somehow independent, right? It cannot be really tested. I'm not saying this is bad or good, I'm just describing it. And the point is that it's certainly, if you have a situation where you have a general statement, or God exists is of course not a general statement, it's a particular singular statement, but if you talk about properties or so, then there may be general statements, and they cannot be tested, or they are not tested at least. And in science, we don't like that, right? In science, things should be somehow related to empirical data. If something is completely unrelated to empirical data, then it does not belong to the natural sciences or to the engineering science. It's something else, right? Maybe mathematics, fine, but then you ask for a proof if you have a statement, or it is something completely different of a metaphysical, religious, or pseudoscientific character, whatever that is precisely, okay? So the demarcation criterion demarcates scientific hypotheses from others, right? And the idea is that scientific hypotheses, they can somehow be tested, empirically tested. This is not a question? No. Now, this is a very important point at this stage of the development of deductivism. In this context, when I speak about the demarcation criterion, to be a scientific hypothesis does not imply that a hypothesis has been accepted or confirmed by science, right? It does not mean that testing procedures were successful and blah, 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 and has been confirmed. That is not meant. It only means that it can be admitted to scientific testing procedures, right? It only says it is a hypothesis that can be tested. It may turn out very soon that it's just false, right? Because the test shows it. But at least it can be tested, right? And there are other hypotheses that cannot even be tested. And the demarcation criteria now demarcates hypotheses that can be tested, turn out to be wrong very soon, perhaps, or turn out not to be wrong, whatever. They can be tested from those that cannot be tested, like certain religious hypotheses, for instance, the metaphysical ones. Right? That's the difference here. It does not say, in that context, scientific hypothesis does not mean, oh, it's a very solid and good hypothesis, right? I believe in it. I would pay any amount, I would bet on it. That's not meant at all. It's only meant it's scientific in the sense that it admits of scientific tests, right? That's less than accepting, but simply saying, oh yes, you are a candidate, I'm sorry you are wrong, you go out again, but first of all, you are a candidate because at least you can be tested. Okay. Now here is the demarcation criterion. Okay, is that point clear, right? It's, so to speak, how to put that in metaphorical terms, it's the entrance fee to enter the domain of science, right? The entrance fee is you must be testable, right? Whether you then survive there, the testing procedures, is a different question. But at least you are admitted to the arena of science, right? And then people will say, yes, do come in. Whereas religious hypotheses are not even admitted to come in, right? Scientists refuse to discuss them as scientists because they say, look, I don't know what to do with you. You are not a scientific hypothesis. I cannot test you, right? Therefore, you stay out. There may be coming in scientific hypotheses, and then scientists will say, after one single test, well, that's rubbish, out again, right? But it's at least scientific in the sense of being tested. Now, here's the demarcation criteria, and you will see what is involved here, and I'm just going to discuss that then a little longer. So we first have the criterion itself. A hypothesis is scientific if and only if it is empirically falsifiable. Empirically falsifiable. And that means that there are empirical circumstances imaginable such that the hypothesis is refuted. Okay. This is a complicated sentence and it's very carefully phrased, so let's go through it. Our hypothesis is scientific if and only if. If and only if means this is a definition. If it's empirically falsifiable. Empirically falsifiable meaning showing its falsity in an empirical way. Empirical meaning involving observational or experimental data. Right? So it's empirically falsifiable, but that means only if there are empirical circumstances imaginable. They must not be real, but you must at least imagine something that would show this hypothesis is false. So a scientific hypothesis, that's a little abstract, I know. A hypothesis is a scientific hypothesis according to deductivism if you can imagine empirical circumstances, certain data coming up that show the hypothesis is false. It's not saying that these data really exist, right, that you can measure it. It only says, well, the hypothesis is of a nature that there are data imaginable, that we tomorrow measure something that shows that the hypothesis is false. Now you'll see that when I give you a contrast, here's a different wording for that, right? Probably a wording you may be more familiar with, that a scientific hypothesis is in principle empirically testable. And the in principle is very important, and the imaginable here. And you'll see soon why this in principle and this imaginable is important. Okay? A scientific hypothesis is in principle empirically testable. Right? That is, of course, you need that in order to then apply testing procedures, you know, the top-down testing procedures that are described in the beginning. If it's not completely clear yet, it's fine, it will become clearer. Now here's a hypothesis, just that you get a firmer grip on what is meant. Here's an hypothesis that is not falsifiable in this sense of the demarcation criterion. That is a metaphysical hypothesis that was held 2,500 years ago by some Greek philosophers. And that says the universe is governed by love and hate. Okay? Once you hear that, you may say, well, it's not implausible. Perhaps it is. Yes. Why not? Now the point is, if you have this hypothesis, imagine circumstances, something that happens in the world that shows that this is false. Okay? Try to imagine something. What is it that could happen in the universe such that it turns out that this is false? Now, let's see, what do we observe in the universe? We do observe stars and galaxies and whatnot, and they move. Let's imagine two galaxies approach each other. Oh, wonderful, they love each other, right? This is a clear case. Or we say, yes, but there's something else, the whole universe expands. All right, they move away from each other. Everything moves away. Yes, clear, there is some hate in the universe as well, right? And they hate each other and therefore they move away, okay? All right, then we have a different situation. Let's take the moon and the earth, right? And they're fairly stable, well, between 300,000 and 390,000 or 400,000 kilometers apart from each other. Stably, you know, the moon running around. Yes, there's a balance between love and hate, right? Yeah, they love each other a little, but not enough, right? They hate each other, and so on. Or you look at anything. Whatever it is, you look at the growth of a plant, and then you say, oh, why does it grow? Oh, it loves the sun, wonderful, it loves water, and it hates, aridity, and it hates ultraviolet radiation, and so on and so forth, okay? So, it turns out that, everything can somehow be described in terms of love and hate, right? Among human beings as well, love and hate, right? And among everything, right? So when you try to imagine what could happen or what had to happen in order to show that this is false, Empirically, you cannot come up with anything, right? You cannot say, if you take whatever it is, you sit down and the chair breaks down, yeah, clearly the chair hates you, right? Or you sit down and say, yes, chair is a good friend of mine, right? It's always love and hate. You can describe everything in terms of love and hate, right? Either love or hate or the mixture between them. Whatever happens, if you have a pendulum, you know, then it loves going in the air and then the air hates it and blah, blah, blah. Just everything, you know, everything can be described as such. So you cannot imagine, it's not the question what you have measured, but you cannot even imagine circumstances, right? Empirical data that show you that this hypothesis is false. You cannot imagine anything, right? Whatever it's always, you can always describe it in terms of love and hate. There is nothing that can contradict that. And that is exactly an example. It's not falsifiable. In that sense, look at it again. Empirically falsifiable, that there are empirical circumstances imaginable, right? You must only imagine them. And here you cannot even imagine empirical circumstances that show that this hypothesis is false, right? That's the point. And therefore, this hypothesis is not even a candidate for science, right? And that is the demarcation criterion says, you, hypotheses, do not even enter scientific discussion, right? You are not even a candidate for science. Why not? Because I cannot imagine anything that happens in the world that I can measure or observe that shows me that you are false, and therefore I don't like you. Right? That's the point. So for a scientific discussion to take place, the candidates must have a certain profile, right? Not every idiot is admitted. And this one is, from the point of view of science, is an idiot, you know, because it doesn't exclude anything. So I don't even have to start to measure anything, right? It doesn't make sense when you say, oh, that's interesting, let's make a few measurements, right? Let's look. What should you measure that shows you that that this hypothesis is true or false? You cannot measure anything because it doesn't collide with anything possible that can come out. You know, whatever you measure, whatever your results are, they're just irrelevant because this thing cannot collide with empirical measurements. And what you want to have in science is something that can collide with empirical data. And that is the demarcation criterion. The demarcation criterion says, I don't want to see anything in science that cannot collide with empirical data. That's got to go out, it will not enter. Right? That's the idea. And that is necessary, I'll do that after the break then in more detail, that is necessary that you can apply the testing procedures that deductivism takes so seriously. Because if you have something that that cannot be tested, of course, then the testing procedures don't work. With that thing here, with that universe and love and hate, testing procedures don't work because they don't get a handle on it and say you are false, because that hypothesis always says I'm always right. You know, I always find a way of love and hate to explain whatever it is, right? And therefore it's not scientific in the view of deductivism. Okay, let's make the break here, 10 minutes. And the horticulture science students, please come here, take a pen with you, and pick a date. And the first one gets the best date, which is, of course, the first date and the first day.